last time we were discussing fuzzy analysis, where we did a kind of a site analysis with a certain criteria. And as you can see here, this was basically our final result. If I take away the background, then you see it clearer. All these gray areas here, they are suitable, and we have the gray values from 0 to the maximum value 0.97. So the darker, the higher the degree of membership to our final result. And in the end, we did a 0.75 cut, meaning we were looking only at those grid cells that have a membership degree greater than 0.75. In fact, for that first, we did a normalization of our result, which exactly looks the same as the original result, only with the difference that in the normalized result, the maximum membership value is 1. And from that normalized result, we took the 0.75 cut, which you can see here are those gray areas around the lakes and in this part of the region, and some are here. So we see that these are our 0.75 cut. Now, this we did with the tools that we have available in QGIS. Of course, you can also do the same thing with the tools available in ArcGIS. And on the website, I have provided you a script, a Python script that will, let me click on it, can we see? Yeah, a Python script that does the same thing. For those of you who are experienced and familiar with Python programming, either in ArcGIS or in QGIS, it would be not difficult to see what's happening here. So you can run that script. The one that I gave you on the website is only suitable for ArcGIS because it contains all the modules and stuff that you need for ArcGIS. For QGIS, it might look a little bit different, of course, and the tools have also different names. Now, today, we are going to look at our fuzzy reasoning example. And for that purpose, we will also later on use a script for ArcGIS Pro, and we are going to use QGIS to solve that problem. But first, let's look at the problem description. So we are doing fuzzy reasoning using GIS. And in this particular example, again, I'm going to use QGIS. And as I said, in the end, I will give you also a script for ArcGIS. Now, what's the problem? The problem is, again, we use the data that we have used so far from the region Boulder in Colorado, United States. And we have the following 4 rules. Rule number 1 says if the slope is flat and the aspect is favorable, then the risk is 1. This actually is, as you can see, this is rules according to the simplified method, because our conclusion is not the fuzzy set, the conclusion is a crisp value. So rule number 1, if slope is flat and the aspect is favorable, then the risk is 1. Rule number 2, if the slope is steep and the aspect is favorable, then the risk is 2. Rule number 3, if the slope is flat and aspect is unfavorable, then the risk is 1. And rule number 4, if the slope is steep and the aspect is unfavorable, then the risk is 5. So what we see here is we have 4 rules dealing with aspect and slope. And depending on the aspect and the slope values that we have in our map, the risk is a certain value according to our rules. So the risk is between 1 and 5, basically. And we are implementing this now using the simplified method. When we recall the simplified method and we look back at our slide where we had the description of the simplified method. So when you look at this, the simplified method consists of 3 steps. The first step is we have to apply our input values, in our particular case for slope and aspect, for every grid cell in our map, and we have to compute the minima according to our rules. So we have 4 rules, we have to compute the 4 minima, and we have 2 variables here. In our particular case, it is slope and aspect. Here we call it x0 and y0. So first we have to compute the minima. Then in the second step, we have to multiply those minima with the conclusion value per rule. So the C1, C2, and so on are the conclusion values, which gives us these conclusions here for every rule. And then the last step is to divide the sum of those the sum of those conclusion values divided by the sum of the minima. And this is what we are going to do here. Now let me go back to the slides here. Okay. So that's the conditions that we have. And I have realized this with a model in QGIS. Those of you who are familiar with QGIS know perhaps that in QGIS you can also use models to solve problems. So you can design models, implement those models, and then you run those models in the same way, or let's say in a similar way as we can use the model builder in ArcGIS. So those of you who are familiar with ArcGIS Pro or ArcMap, you are definitely familiar with the model builder. And you know the model builder works in that way that you have the data and you have processes that you run. So you connect the data with the process. The process is usually it's a tool from the toolbox, which gives you some results, and that you can, so graphically you build your model and then you run it. And the advantage, of course, is that you don't need to call up all the tools individually, because you put them all into your model and you can make modifications pretty easily by adjusting the model and then validating and running it again. In the same way, you can do it in QGIS. It just looks a little bit different in QGIS than it looks in ArcGIS. So this is the model that I have already built, and we will go through that model. So basically, it works in that way that we start with our elevation model, because that's the only thing we need here. We need the elevation model, and from the elevation model, of course, we can compute slope and we can compute aspect. Sorry. And that's the only things we need. We need the slope and we need the aspect. Then we need to compute the fuzzy sets for flat slope, steep slope, flat slope, steep slope, favorable aspect, and unfavorable aspect. Then we have to compute the minima according to our rules, which I call here M1, M2, M3, and M4. I will go into more details a little bit later, so don't worry now. After that, we compute our C values, the C1, C2, C3, C4 for our 4 rules. We create constant rasters for the conclusion values. You remember in our rules, we had conclusion values 1, 3, and 5. So we create a constant raster, one which has only values of 1, another one which has only values of 3, and then a third one which has only values of 5. And these constant rasters we can then use to multiply the constant raster, for example, for rule number 1, the constant raster with value 1, and the M1, the minimum that we computed for our rule number 1. And we do that for every rule. And then the last thing that remains is we just need to compute the sum of our C values, which I do here. This is the sum of the C values. Then we need the sum of the M values. And the last step is the division of the C values by the sum of the C values divided by the sum of the M values, which gives us the final result. So it's a pretty straightforward and simple model, but let's walk a little bit through the individual steps. So first of all, as we said, we need to compute flat slope. As we know already from our previous case study, to compute the slope is pretty easy. In QGIS, there are a lot of tools in the raster terrain analysis, for example. Then we have the slope, and then we use in our case, again, I use for simplicity, I use the linear membership function to compute the fuzzy slope using the fuzzy raster linear membership tool. And we have defined, okay, I should jump back perhaps to our previous slides where we had the same example doing it with Excel. Let me see, where do I have it? Here, yes. We defined a flat slope with that membership function so that from 0 to 20, the membership degree decreases. So the highest membership degree is at 0 degree slope, and the 20 degree slope, the membership degree is 0. And for steep slope, we define that up to 5 degrees slope, it's definitely not steep. Then it increases and becomes 1 at 30, at the slope of 30 degrees, and from there on it stays 1. And for the favorable aspect, we defined a triangular membership function where we said, and again, recall aspect is given by degrees from north. So if we have 0 degrees due north, 90 degrees is due east, meaning up to 90 degrees, it's definitely 0, a favorable aspect. Then it increases to 180, meaning from east to south, it increases. At due south, the membership degree is 1, and then it decreases until west, 270 degrees, and from there on, it stays 0. And then we look at the unfavorable aspect, which I simply define as the complement of favorable aspect, meaning it's 1 minus the membership values for favorable aspect. So these are the membership functions that we use here. And when I go back again to our example here, then the flat slope is defined with the linear membership function for fuzzy raster with the parameters 20 and 0. And again, you might recall, or you should remember from last time, we can create ascending and descending membership functions with this linear membership tool. We can create descending membership functions when we put the higher value at the low bound and the smaller parameter value at the high bound. So 20 comes here and here comes 0. That creates our decreasing membership function for flat slope. Actually, the result then will look like this, as you can see here on the right-hand side. Then we need steep slope. So steep slope we defined in such a way as I showed you on the membership function on one of the previous slides, with the parameters 5 and 30. So up to, since this is an increasing membership function, we use the lower parameter value for the low bound and the greater parameter value for the high bound. So 5 here and 30 here. And then we can run this tool also, and which gives us this result, where you can see, of course, remembering the topography of that area, that towards the west, we have the foothills of the Rocky Mountains where we have steeper slopes. So, and towards the east, it's pretty flat terrain. So, of course, there the membership values to steep slope are low, meaning very close to white and light gray. And towards the west, when we have the higher mountains and the steeper slopes, the membership values get greater, meaning in our color scale, the color gets closer to black, dark gray and black. Now that's the steep slope. And then we need to compute our favorable aspect, which we do according to the membership function that we defined, the triangular membership function. Since neither QGIS nor ArcGIS Pro or ArcMap has a tool for triangular membership functions, we can just create it by using two linear membership functions and the intersections of these two linear membership functions. Again, with the parameters 90, 180, and 270 for east, south, and west. Now, in QGIS, we do it again with the fuzzy raster linear membership. First, we create the ascending part from 90 to 180, meaning the membership degree increases from east to south, from 0 to 1, and then the descending part with the parameters 270 and 180, meaning from south to west, it's decreasing and stays 0 then at 270 degrees, or due west up to north again. And finally, we just have to compute the intersection of these two membership functions using the minimum operator, which gives us then our result for favorable aspect, which looks like this, and it looks basically exactly the same. It's the same that we did in our previous example, where we were dealing with favorable aspect. The next step, which is new, is the unfavorable aspect, which we defined as just being the complement of favorable aspect, meaning 1 minus the membership values. And again, this is a pretty straightforward thing. We create a constant raster 1, which we use for the subtraction of the values. So there is a tool, create constant raster layer, where we take as the extent and the coordinate reference system of our elevation model. So in other words, the new constant raster that we create will have the same extent as the elevation model, and it will have the same coordinate reference system as our elevation model, and it will have the same pixel size as our elevation model, which is 10. So our pixel size for the elevation model is 10, which I already mentioned also last time in our class. And the constant value that we want to give to this raster is 1. Okay, with this tool, we create the constant raster, and then we compute the complement by using the raster difference tool in QGIS, where we use as input the constant raster with the value 1 that we just created, and the raster that we created for the favorable aspect. And we call it unfavorable aspect, and then it will give us this result. So you can see here a lot of dark areas. These are all those areas that have an unfavorable, a high membership degree to unfavorable aspect versus the favorable aspect that we have here. Okay, and then we need to apply our simplified method, meaning first we have to compute all those minima. And if you should remember from the discussion of the simplified method, we have to take our rules. And if I jump just back here, our rule number 1 has flat slope and favorable aspect. So we have to compute the minima of flat slope and favorable aspect. In this particular case, you can see here, I used the tool fuzzy intersection, and with the method using the minimum of the two values, that's a tool in QGIS, and we select flat slope and favorable aspect as the input rasters or the grids that we need to compute the minimum of, and the result we call M1. And we do the same thing for the second rule, for the third rule, and for the fourth rule, where for the second rule we have to use steep slope and favorable aspect. For the third rule, we have to use flat slope and unfavorable aspect. And for the fourth rule, we have to use steep slope and unfavorable aspect. So we have to do that, as you can see here in our model. We have 4 times this fuzzy intersection. For M1, we have our flat slope and the favorable aspect. For M2, we have the steep slope and the favorable aspect, and so on. And in the next step, we have to compute the conclusion values, taking the conclusions of our individual rules with the minima. So we have to compute the product of the minima and the conclusion values of every rule. Now again, for the first rule, it would be M1, the minimum that we computed for the first rule, multiplied with the conclusion value of the rule number 1, and the conclusion value of the rule number 1 was 1, so it will be our constant raster number 1. For the second rule, the conclusion value is 2, so we will use, where is my 2? Did I miss it out here? 1, 3. Wait a moment, is it 2 or 3? Obviously, I used the conclusion value 3 instead of 2 here, so I will. You see, when you are doing these things, sometimes you detect some mistakes. So let me see. Obviously, in my model, I use the conclusion value 3. On my slide, I said the conclusion is 2. So let me check what we did in the Excel example. Which rules did we use there? And then I will later correct it and update it. Okay. Okay, it is 3. So in our Excel example, we use the conclusion value 3. So I just made a mistake here in the rule. Let me go back to the rule. So the conclusion is 3. I will update the PDF of the slides on the website later on. So the rule is 3. the conclusion value is 3. So I did it correct in our model here because I was using the value 3 for rule number 2, and then we still have the conclusion value 5, so it's 1, 3, and 5. Okay, and we do that for every rule. So for the first rule, m1 times 1. For the second rule, m2 times 3. For the third rule, it's m3 times 1. And for the fourth rule, it's m4 times 5, which gives us these values. So that's what we do here in step number 2. And then the final step, step number 3, is we have to compute first the sum of our C values that we computed, then the sum of our M values, and finally we have to divide the sum of the C by the sum of the M values. So again, there is a tool in QGIS that's called raster sum, and there is a tool which is called raster division. So we use this tool for raster sum, adding up our 4 C values. These are 4 inputs selected, and we call it sum CI. And the same we do for our M values. There we would take all our M values, we call it sum MI, and then we call the raster division tool, where we divide the sum of the C values divided by the sum of the M values, and we call the final result fuzzy risk. And in the end, it should look like this, where 1 is obviously the lowest risk and 5 is the highest risk. And the higher the risk, the darker the color. So the gray values from white to black. And you can see here in this final result that again, of course, towards the east, the risk values are, according to our rules and slope and aspect, are pretty low, and they are getting higher in the mountainous areas. And also what we very clearly see here, the valleys. Here, this is the value in the valleys. The risk values are pretty low because, of course, in the valley, the slope is pretty flat because it's usually a flat area in a valley, and in a valley, and the aspect is also pretty good because if it's flat, the aspect is also, of course, also favorable. So this is how it would run. And now let's have a look at our GIS. Did I open already the model? No, let's open. Okay, I created a model which I call fuzzy reasoning. I opened this model so you can see how it looks like. So the models, I take it that those of you who are using QGIS know how to use the model designer in QGIS, so I don't need to explain the details. You basically add your data and then you add your algorithms, as they are called here, from the tools that you have on the left-hand side. So, for example, for the slope, you just have to enter the parameters, and for example here the constant raster, again we just enter our parameters and so forth. So this would be our let me now just zoom to the full extent. Okay, and now we have here our model. To perhaps see it better, we can do it this way. So this is our model, and when I can to be sure that there's nothing wrong in it, I can validate it. So it says the model is valid. And of course, then I can run the model. Here, as you know, for those of you who use QGIS, you know that you can here enter some names of the model parameters. I don't need to do anything here, anything particular. So this is all okay. And finally, I just run this model. And if everything is fine, the model should run till the end. Just waiting a few seconds until it's done. It just takes a while because I still have the ArcGIS Pro open, which is also consuming memory on my computer. And there is still a lot to do with these tools. And my computer is nearly 4 years old, so, but it's still working, that's fine. So 63% done. Almost through. Okay, almost there. Okay, that's it. Let's close this. Okay, and then we should have here our results. So the only thing I need to do is I need to clean up the display a little bit, because all the intermediate results are also there. So I don't want to display the M values. I don't need them. I don't need the C values to display. I also don't want the sums. So, but what I want to display is our unfavorable steep slope, flat slope, favorable aspect, and of course our final result. So let's click this away. So that should be our final result, but the color scale is inverted, so I will make it from white to black, from 0 to 1. So that's our final result. And if we compare it to our slides, it should be pretty much the same, yeah, as you can see here. So this is the final result in my slide, and this is the final result that we just computed. And of course, if we wish, we can also show our results for slope and aspect. So again, adjust the color scale. And there is one more. Okay, so then we have here our flat slope, our steep slope, favorable aspect, unfavorable aspect, and again, our final result. So, of course, you could have done this also by calling the individual tools one after the other, as we did last time with our fuzzy site analysis, where I did not build a model, where I used the tools one by one to achieve our result. Here we have a model. What I will do is I will provide you with a picture of that model. I will export that model as a PDF and put it on the website, and I will also export this model as a Python script for QGIS, which I will also put on the website. Of course, the only thing you need to do when you want to use this model is you have to adjust the input data, because on your computer the data will be somewhere else than they were on my computer. So that's why I will comment out the references to my data, and you will have to add the correct references to your data. And in the same way, we will go through that example using now also then ArcGIS Pro, building a model there also, and I will also provide you a Python script that does the same thing in ArcGIS Pro or in ArcMap. The script is basically the same for ArcMap and ArcGIS Pro. There is, as far as I remember, no difference. It should run on both systems. Now, let me go back to what I'm going to do now in the second part of today's class is I will, for those of you who are working with ArcMap or ArcGIS Pro, I will go through the same problem that we just did for QGIS. I will do it in ArcGIS Pro. And again, for those of you who are using ArcMap, it works pretty in the same way. So again, what we have here is we have our base map that I have prepared already with our roads, major roads, parks, water bodies, and of course we have our elevation model that we need. So what I'm going to do now is I will go through the same problem using the model builder in ArcGIS Pro. So I'm using the model builder, I create a new model, and of course what we need is we need the elevation model. So I'm putting the elevation model in here, and then we need tools. So I'm opening the toolbox. What we need from the toolbox is the spatial analyst tools. And of course, first we need to compute the slope and the aspect. So it's under the surface tools. So we need to compute slope. We need to compute aspect. And okay, that's our input raster for the slope, and that's our input raster for the aspect. So that's slope and aspect. And then we need to create our fuzzy sets, flat slope, steep slope, favorable and unfavorable aspect. For that, we use the overlay functions, the overlay tools in the spatial analyst. You see here the tool fuzzy membership. So we need the fuzzy membership tool, and we will also need it for the aspect. For the aspect, I would need it twice because, as I said, the same situation with QGIS. For favorable aspect, we use a triangular membership function, which we create by using two or combining two linear membership functions. So I need two membership functions for the aspect here. Now, but first let's look, actually I need another one for the slope, because we have flat and steep slope. So let's first look at the flat slope. We make this the flat slope, and it should be I take the linear membership function, and for flat slope, you remember we used the parameters 0 and 20. So at 0 degree slope, the membership is the highest. At 20 degree slope, it's the lowest. And it's a descending membership function. So we have to use the 20 here for the minimum value, and the 0 we have to use for the maximum value. It's the same thing as in the QGIS tool for the linear membership function. In ArcGIS, you could add here a hedge. You know, the hedge is like vary or somewhat. We don't use any hedge here. So that would be our flat slope. Let me perhaps rename this, that I know what we are doing here. That's the flat slope. And now we are computing the steep slope. Again, we use our slope here as an input raster. And for the steep slope, we had an ascending linear membership function. So I have to choose the linear one. And we said it's between 5 and 30. So at 5 degrees slope, it starts increasing. At 30 degrees slope, it becomes 1 and stays 1 there. And that's an ascending membership function. So it is our steep slope. I will rename it to steep slope. Okay. And now we have to create our favorable aspect. The favorable aspect, as I said, consists of two linear membership functions. One will be the ascending part, I call it ASC, and one will be the descending part, DESC. Okay, now we have to enter the parameters. Again, we use a linear function. And I said the ascending part, membership to favorable aspect is 0 up to 90 degrees, which means east. Then it increases and becomes 1 at 180 degrees. And then we need the descending part, again, a linear membership function, which descends from 180 to 270, meaning from south to west. And since it's a descending membership function, again, we have to swap our parameters. So put the higher value at the minimum and the lower value at the maximum. This is then our descending part. Fine. Now, as I said, we need to combine them, meaning we have to use an overlay, fuzzy overlay, using the intersection. What is sorry about this? Okay, let me see what's wrong here. Okay, that's the fuzzy overlay. Yeah. Okay, input rasters. And we need the combination or the overlay of these two rasters, and we use the end as the overlay type, which means it's the intersection. So this gives us, as I rename it, and this would give us the favorable aspect. Fine. So now let's go back a little bit and arrange our model a little bit nicer. So what else do we need? We need the unfavorable aspect, which we say is the complement of the favorable aspect. So it's 1 minus. So we use the mass, one of the mathematics tools, the math tools, and we use the minus tool, which computes the difference of 2 rasters. So I use the minus tool. And it is our favorable aspect is the raster number 2, because the raster number 1 is our constant value 1. So 1 minus the output raster, or 1 minus the favorable aspect, gives us our unfavorable aspect. Okay, once again, let's lay it out in a nicer way. So we already have now everything that we need for running our rules. But what I'm going to do here is I will just save the model, so that if something goes wrong, I can call it up again. Nothing is lost. So now we have to compute, we have to go to step number 1, meaning we have to compute the minima according to our rules. So if we recall, it was for rule number 1, it was flat slope and favorable aspect. So we have to compute the minima, which again we can realize using a fuzzy overlay. Again, we can use the end function, because the end is the minimum. So we, oops, now I clicked away my toolbox. Let's call it up again. So we need a fuzzy overlay. We need it actually 4 times here. Let's move that over here. So we need flat slope, and favorable aspect. I call it M1. Then for rule number 2, it was steep slope and favorable aspect. So it is the steep slope. Where is my steep slope? It's here. And favorable aspect. Oh, sorry. Steep slope and favorable aspect. This is the favorable aspect. So fine. And I call it M2. Then rule number 3, flat and unfavorable. Again, flat and unfavorable. with M3. And finally, rule number 4 is steep slope and unfavorable aspect. So steep slope and unfavorable aspect, and call it M4. Okay, now we have our minima. And again, let's just lay it out in a different way. So fine, now we need to compute the conclusions by taking the multiplication of the minima and the conclusion value per rule. So for that, we use the multiplication. Again, under the mathematics tool, we have a tool which is called times. Times is multiplication. So again, we need that 4 times, because we have 4 rules. Okay, now for the first rule, the conclusion value is 1. So we need to multiply M1. Sorry, this is the M1 result. So M1 with 1, constant value 1. And we call it C1. Then for rule number 2, the result value is 3. So we have to multiply our M2, the result here, M2, with 3. And I call it C2. Then for rule number 4, it was 1, and for 5, it was 5. Okay. So for rule number 3, we have to take the M3 and multiply it with 1. Call it C3. And finally, we have to multiply our M4 with 5. And we call it C5. Okay, now let's just the layout. Okay, and then finally, what we need is the sum of the C values and the sum of the M values. For that, where is this? I think it was no, weighted overlay? No. The weighted sum, we use the weighted sum tool. Again, we need 2 of them. So the weighted sum tool works in that way that it sums up rasters according to their value, and you could give a weight to every single input raster that is summed up. So our weight will be 1. We don't give any weights, and the values will be the field that contains the values that need to be summed up is called value in our particular case. So what we do is we sum up first our C values. So where is my C1? That is here. C1 with our C2, the C3, and in fact this I misnamed, it should be C4 here actually. I don't have 5 rows, we have only 4 rows. So this input raster, and then, okay, you see the value is already here. The weight is 1 by default. So we don't have to do anything else here, except now summing up our M values. So this is my M1. The M2. The M3 is here. And the M4 is this one. Again, everything is set. Let me lay it out a little bit better. So, okay. Okay, now I just have to rename it. These were the so that I don't make a mistake. So these are the C values. Okay, so this I rename as sum of CI, and this I call sum of MI, so the sum of the minima. And now we need to divide the sum of the CI by the sum of the MI, and there again we have a mass function, or a tool, I should rather say, mass tool divide. So we divide the sum of the C by the sum of the M. And that should be our final result. Okay, so basically our model should be ready. Let's just save it to be on the safe side. Okay, for those of you who are familiar with ArcMap or ArcGIS Pro and the model builder, you know, basically know the results are not shown on the display. So I have to add, I want to see, for example, the steep slope. I want to see, so I add it to the display. I want to see the flat slope. Where is the flat slope? Oh, here. I want to see the flat slope. I want to see the favorable aspect. And I want to see the unfavorable aspect. And I want to see, of course, the final result. So now we have our model here. Let's validate it. Okay, looks fine. And now let's run it. Okay, again, this will take a little while. You can watch here the progress. It will take again a little while because we still have the QGIS open and PowerPoint, some other stuff. So we are now at process 7 of 19. And on the left-hand side here on this bar, you can see already the results popping up that I want on the display. So we have already now a slope and aspect. Okay, we are more than halfway through. Okay, already at 15 out of 19. Okay. Are we done or not? There is an error. Let's see. What was it? Something went wrong here. What does it say? Okay, something's wrong with the parameters. I have to figure out what's wrong. It was which tool? Steep slope? No. Fuzzy overlay. Fuzzy overlay. Okay. I clicked validate model. It takes a while. Okay, now. Okay, so let's have a look again. Whenever you do something live, so to say, then most likely things go wrong. So I do it step by step. Just call every tool. Okay, aspect is done. The ascending part. The descending part of the favorable aspect. Okay, sorry, now let's look at the intersection. Okay, so the favorable aspect seems fine. Slope. Okay, so slope is okay. Now let's see the steep slope. Okay, the steep slope, the flat slope. Okay, and the unfavorable aspect. Okay, so far it looks fine. Okay, then the M1 was what? M1 was the flat slope and the favorable aspect. Okay, the M2 was the steep slope and the favorable aspect. There's something wrong here. Okay, M2 was what? M2 is steep and favorable. Okay. So it should be the steep slope. And the favorable aspect. Okay. M3. M4. Okay. The C values, C1. Okay, C2. Okay, still running. Okay, C3. And C4. Yes, still no error here. The sum of the C values. Okay, the sum of the M. And the final. Okay, so let me check one thing. Okay, that's correct. That's one. That's also correct. And this is also correct. Okay, now let's have a look at our result. Well, something is not quite okay here in this model. It doesn't look like our original thing. Well, I would have to go through the parameters again. The principle is the same as we did in QGIS. But what I also did is I prepared a Python script, which I'm going to run now. And hopefully that will give us the result that we expect. I just have to check. Oh, I called it because I have one with my correct passes and another one with the commented out passes. So let me just check here. This is it's called, okay, it's called, in my case, it's called risk analysis. That will be the one with the correct passes. And if I run that, hopefully it will succeed. So still running. By the way, this script is already on the website. So you could already copy it and try it out with the passes to the data that you use. Okay, it's almost done. It is done, yes. Okay, and this is our final result here. Okay. That should look like we expect. Compared to our slide here. Yes, it is what we expected. So the script is okay. This is the script that I used. So what you see here is here I have the pass to my data, which of course you will have to change. What you have is this here, so you have to complete these passes here. And again, what this script does is very simple. It first computes slope and aspect, then flat slope using the linear membership function. It's called fuzzy membership. Then the steep slope, then the favorable aspect using a map algebra expression, the unfavorable aspect using the complement, and then computing the minima by using the fuzzy overlay of the corresponding values for the rules 1 to 4 using the fuzzy overlay tool. Then we compute the step 2 by multiplying the minima with the conclusion values. So M1 with the conclusion value. Okay, here there is again some slight mistake, because our rule number 2 had as a conclusion value 3. I just see it here. I used 2 here, so that should be a 3. I will modify that later. This is 3, yes, then 1 and 5. And then just the final result as the sum of the C values divided by the sum of the M values. And I store the result as a raster or as a grid that I call fuzzy risk. So I save it, and I can, if I wish, I can do it again. And I can run it again now with the correct parameter. And that basically would bring us to the conclusion of our